Hello, I'm Truong Pham, a senior scientist at NVIDIA. Today I am going to talk about our paper entitled MV Autonet, Fast and Accurate 360-Degree 3D Visual Perception for Self-Driving. Self-driving technology offers the potential to enhance road safety by reducing human errors, increase transportation efficiency through optimized traffic flow, and provide newfound mobility opportunities, particularly for individuals with limited mobility or accessibility challenges. Let's talk about the brains behind autonomous driving. Its software stack, which is composed of multiple components, and today we're zooming in on perception. This is where the system takes in data from sensors like camera images to spot and understand what's around, and constructs a real-time 3D map. Those 3D information help the car predict and plan its moves, ensuring it navigates smoothly and makes smart decisions on the road. Our goal is to craft a perception network guided by key principles: precise 3D perception, extended range detection, up to 200 meters, efficiency at its core, operating in real time on edge devices, like the NVIDIA DRIVE Orin system on chip, ensuring seamless responsiveness, resilience to camera variability, maintaining robust functionality even in the face of camera dropouts, holistic machine learning, no need for post-processing networks, performance scales effectively with data volume, adaptive scalability, simple customization for diverse vehicle platforms highlights the network scalability. The current state-of-the-art 3D perception methods tends to emphasize detection accuracy as a primary metric. However, in this pursuit, critical considerations like computational efficiency, compatibility with onboard chip deployment, resilience to potential sensor mounting deviations, and adaptability across diverse vehicle types are often overlooked. The significance of achieving a balance among these factors cannot be overstated, as it directly influences the practicality and effectiveness of 3D perception systems. NV Autonet emerges as a cutting-edge bird's-eye view perception network, crafted to meet the unique demands of automated vehicles. NV Autonet takes camera images as input to predict 3D signals, such as obstacles, free spaces, and parking spaces. One of its standout features lies in its proficiency in identifying objects at substantial distances, up to 200 meters. NV Autonet's architecture strategically leverages efficient multi-layer perceptron and convolutional networks. Trained on an extensive proprietary dataset, NV Autonet achieves high perception accuracy. It operates at a remarkable speed of 53 frames per second on the NVIDIA DRIVE Orin system on chip. NV Autonet also demonstrates resilience to sensor mounting deviations, adapting flexibly to diverse car models, and excels in accommodating various vehicle types. Let's dive into MV Autonet's architecture. Picture this. It uses a bunch of cameras to give a complete 360-degree view all around, and they come with camera calibration parameters. The images from these cameras go through 2D encoding to pull out important visual features. Then these features are turned into something called bird's eye view, BEV features. Each camera's unique BEV features are fused into a big map, which then goes through a BEV encoder to extract high-level BEV features. After that, this encoded BEV feature map goes through multiple task decoders to output 3D stuff like obstacles, parking spaces, and free spaces. In this work, we heavily lean on convolutional neural networks for both the camera and bird's eye view backbones to ensure high efficiency. The overall network architecture draws inspiration from ResNet without skip connections. To strike the perfect balance between accuracy and efficiency, we employed neural architecture search to discover the optimal configuration of wide and deep channels. Now let's tackle a tricky problem, turning the 2D images into a 3D or bird's eye view perspective. The state-of-the-art methods often hinge on predicting pixel depths to construct a 3D volumetric feature map, subsequently collapsed into a BEV feature map. Unfortunately, these methods tend to be both memory and computation intensive. In contrast, our approach transforms image features into BEV features without the need for constructing a resource-heavy 3D feature map. In particular, each image column undergoes independent transformation into BEV using simple multi-layer perceptron layers. Camera intrinsic and extrinsic parameters are encoded into BEV lookup tables, which play a crucial role in fusing multiple camera features into a unified BEV feature map. Let's talk about what NV Autonet can predict. It predicts a bunch of things all at once, like 3D obstacles, 3D parking spaces, and 3D free spaces. For obstacles, it is 9 degrees of freedom cuboids. Parking spaces are represented by oriented boxes. And for free spaces, it uses a radial distance map that tells us how far things are. For all tasks, we adopt a set prediction formulation to remove needs for prediction post-processing. Now let's talk about multitask training. Here's the thing, these tasks are all a bit different. So training them by simple adding up their losses doesn't really work well. Instead of just giving equal weights to all the tasks, we adjust how much attention we give to each task while training. It means the loss weights for different tasks are adjusted automatically on the fly, once per epoch. The idea is simple. Loss weights are computed inversely proportional to their loss sums over the entire training set. NV Autonet is deployed using NVIDIA TensorRT and tested on the NVIDIA DRIVE Orin platform. Except the 2D to BEV transformation and fusion parts which run on GPU, the rest run on DLA Deep Learning Accelerator. The total latency is only 18.7 milliseconds, which translates to a remarkable frame rate of 53 FPS. We train and test NV Autonet using our in-house datasets. The datasets consist of real, simulated reality, and augmented reality data. In total, there are 2.2 million training scenes, 400K validation scenes, and 177K testing scenes. The data was collected from more than 20 countries, and from different weather, lightning, and road conditions. We perform extensive experiments to evaluate the performance of NV Autonet using standard metrics such as MAP, F1 scores, and regression errors. The overall MAP score of 3D obstacle detection is 0.46. The network excels in detecting vehicles, attaining an AP score of 0.64 while it faces challenges in identifying persons pedestrians, with an AP score of 0.35. When focusing solely on a safety region, within 100 meters ahead and behind the ego vehicle and 10 meters to its sides, the MAP score notably improves to 0.59. For free space detection, the network achieves relatively high accuracy overall. For parking space detection, the overall detection accuracy is high. However, the parallel parking space category exhibits low performance, which can be attributed to ground truth labeling intricacies. As mentioned earlier, NV Autonet is a multitask network. Here we show the performance comparison between the multitask model against independent single-task models. It's observed that obstacle and parking detection accuracies hold up comparably to those achieved by the single-task models. Although the free space task experiences a performance drop, its accuracy remains commendable. This outcome underscores the substantial efficacy of our proposed multitask loss balancing algorithm. Adaptability to many different vehicle lines is vitally important for autonomous driving mass production. We demonstrate that deploying our perception model on a distinct platform doesn't necessitate extensive model redesign or extensive data collection. Remarkably, achieving satisfactory results only requires fine-tuning the model using a limited training dataset. Finally, we show qualitative results of NV Autonet. Also, it is worth mentioning that NV Autonet has been deployed and tested on real roads. Thank you for your attention.